Sea level rise is a topic that has had a lot of press in the last few years as a major consequence of global warming. Boston, Cambridge, New York, and San Diego are a few of the cities that have begun to study construction methods along the coast in anticipation of future flooding. We hope that today's event gets the ball rolling for future discussion about climate change and inspires people to start thinking about living more sustainably. Dr. Ellen Douglas is a hydrologist and engineer with broad expertise in the analysis of water-related issues. Her research utilizes computer modeling and data analysis to define and support sustainable management policies and practices related to water resources and climate change adaptation. Chris Watson and Professor Ellen Douglas were engaged by NOAA 3 years ago to study sea level rise in the Boston area. They were just refunded by NOAA to take their research on Everett and East Boston to the next level. I'm grateful for Chris and Ellen's time today and excited to see their presentation.
As was noted, we've done some research on the impacts of sea level rise. Can everybody hear me okay? Sea level rise in the Boston area, so I wanted to share some of that work with you. But before I get to that in particular, I wanted to talk a little more broadly about what climate change means and why we are concerned about it. But first, I always like to talk about a few of the misconceptions that I know that are out there in the public. One is that we shouldn't worry about CO2 because we all breathe out CO2. CO2 is a natural part of life, and it's a naturally varying cycle, all of which is very true. Here is a record of CO2 concentrations in the atmosphere since about 800,000 years ago. And you can see that it varies. It usually stays between 200 and 300 parts per million, which is just a concentration measure. And you can also see that over this nearly million-year record, the maximum concentration has not exceeded 300 parts per million. That's that dashed line right there. But now, recent observations as we burn fossil fuels, and we'll talk about what fossil fuels mean in a minute, and emit CO2, additional CO2 into the atmosphere, we're seeing a rise in those CO2 carbon dioxide concentrations. In 2008, it was around 390. Currently, it's very close, if not at 400 parts per million. So already we're at a level that's about a third or more above this 300 parts per million threshold that we've seen over the last million years. Projections from computer models that try to take into account the kind of lifestyles that we have and that other countries are trying to achieve by burning fossil fuels and land use change, things like that, put our future concentrations anywhere from 2 times to 3 times the current level of CO2 in the atmosphere. So you can see that even right now we're sort of in uncharted territory, and we're heading even farther into that uncharted territory in the future. Why is this important? Well, we have this beautiful carbon cycle. If any of you are old Star Trek fans from like the real original Star Trek, you may remember that they talked about, oh, there's carbon-based life forms on this planet. Carbon is a part of anything that has life in it. So carbon is a part of our bodies, carbon is in the atmosphere, carbon is in the rocks, it's in the ocean, it's in the trees and the animals that live on the land. So we have this wonderful large-scale carbon cycle and the carbon is recycled at different rates depending on what part of that cycle that carbon molecule happens to be in. So we have carbon that's actually taken up by plants. As you know, plants and trees take up CO2 to build biomass, and then they give off oxygen. But as those plants biodegrade, if they die and biodegrade, then that CO2 is put back into the atmosphere. The ocean absorbs a lot of CO2, and naturally there's an exchange between the ocean and the atmosphere. And then, but the problem that we have with the CO2, with the carbon cycle right now, is we're causing an imbalance by burning fossil fuels. Does anybody here know how to define what the definition of a fossil fuel is? Why do we call it a fossil fuel? Okay. And what does that mean? It's buried deep in the earth, right? So fossil fuels is just carbon that was part of life millions and millions of years ago. But that carbon has been buried deep into the ground and basically separated from our current natural carbon cycle. So the carbon cycle we have right now, it has been developed without these really old fossil carbon molecules. And by digging out the oil and the coal and the gas and then burning it and emitting that carbon back into the atmosphere, what we're doing is we're pumping in more CO2 than our current cycle can handle, and we're imbalancing that cycle. So it's not that CO2 is not a part of the natural cycle, it's just that we're sort of dumping more in than the current cycle can handle. And so we're imbalancing parts, like we're causing more carbon dioxide to be dissolved in the ocean, which is causing an acidification effect. And we know that CO2 is one of several so-called greenhouse gases that absorbs heat from the sun as it's re-radiated back from the earth. And that the whole greenhouse effect is a very good thing, because otherwise our average temperature would be like -10 or -50, something like that. So the greenhouse effect makes Earth very habitable, but as we increase that level of CO2 in the atmosphere, we increase the thickness of the blanket, basically, that traps the heat, and so we increase the temperatures within the atmosphere. So that's one of the concerns with the rising levels of CO2 in the atmosphere. Another misconception that people often have is that there's no real evidence of climate change. I heard Ben Stein say that a little while ago on TV, and I'm thinking, what? Like, are you looking? So, you know, we've seen, there are many, many reports that come out and say, you know, the last decades worth of years are hotter than we've seen in the time that we have been observing these things. We've also noticed that ice caps and glaciers are disappearing at unprecedented rates. Sea level is rising, and that is a natural cycle, but it appears that it's accelerating above that natural cycle. We are beginning to observe many more extreme events than we have in the past: heat waves, hurricanes, precipitation extremes. It seems whenever we have a big rainstorm event in New England, or in this part of New England, Quincy is always in the news about some flooding. So you guys are probably very familiar with the impacts of some of these extreme events. Droughts, snowstorms, although this year we were certainly saved from any snowstorms, but we made up for that last year. And all of these observations, all of these things that we've been seeing is consistent with what climate change experts and what the climate models have been predicting would be a consequence of climate change. And so you really can't say that there's no evidence for climate change. We're observing these things right now as we speak. So another misconception is that we as humans are too small to really impact the natural cycle on a global, natural systems on a global scale. But in fact, maybe individually that may be true, but collectively, when there's 6 or 7 billion of us on the planet, we actually have a fairly large impact. We've taken 1/4 of the Earth's surface and converted it to agriculture. That's a lot of land. We have stored a large amount of water behind dams. About 25 to 30% of the sediment that would flow to the oceans through the rivers in the natural cycle is trapped behind these dams. And we've fragmented about 80% of the large rivers around the planet with these dams. So we have large impacts on a lot of systems. We as humans appropriate or use up about 15 to 40%. Of course, these numbers are really hard to nail down exactly, of what's called global net productivity. And that's just basically the biomass that we eat, either indirectly or directly. And so as humans, we really have made huge impacts on the planet. And so it's really not out of the realm of possibility that we could have a large-scale impact on the atmosphere as well. As a matter of fact, some geologists now are calling our current time the Anthropocene, because, and anthro being human. So we're having such an impact on the planet that they've named a new geologic time frame after us. So one of the facts that I would like to present to you is that climate change is underway. This is actually some reporting from the IPCC. Do you all know what the IPCC is? The Intergovernmental Panel on Climate Change. It's a group of thousands of scientists that get together, and they're getting together right now to come out with a new report. They get together, they look at all the research that's been done to summarize the most recent understanding of climate change. And so in 2007, They came out with their latest report. They have another report they're working on right now, which will come out in 2014. In the 2007 report, and they've been coming out with reports since like 1990, so for the last 20 or so years, they said that it's unequivocal that the Earth's climate is warming. Now, the reason I put this word in red, and also it's very likely that human emissions have caused some of these or most of these observations of increasing global temperatures. The reason I put these in red is when the IPCC puts out their report, so the scientists get together, they write a report, and then the diplomats from all the countries that are represented get together and wordsmith. And so by the time this report comes out, each and every word that's in that report has been argued with, and it has to come to agreement. Everybody has to come to agreement before this report is put out. It's a very arduous process. And so every word, like unequivocal, very likely, less likely, has a specific probability associated, a specific level of confidence. So when they say very likely, that means they have greater than 90% confidence that that statement is true. When they say unequivocal, it's just off the charts. There's just no question. So this was the first time that I saw, in looking at IPCC reports, wording so strong. And so I was very impressed by that. So how is our planet responding? Well, we know that the average temperature around the planet has been increasing. You can see that it's increasing. But what's also increasing is the rate of increase. So it's increasing at a faster and faster rate. As a consequence of that, the ocean is actually absorbing some of that heat. Now, the ocean takes up 70% or more of our planet, so it's a very large surface area. And so as the atmosphere warms, the ocean begins to warm too. So you can see there's this increasing trend in ocean temperatures. And one of the consequences that we're going to talk about a little bit later is sea level rise. So this shows a map since 1800 of the level of the sea, and this is actually sea level change, so it's the rate of change from year to year. And between 1800 and 1900, it was pretty steady, changing a little bit. And again, natural sea level rise is a natural process. It happens, sea level goes up and it goes down. It's a fluctuating natural process, just like the CO2 concentrations. But in the 20th century, as we were adding more CO2 and more greenhouse gases to the atmosphere, causing more warming, and then some of that warming was being absorbed by the water begins to expand. And so as the water is expanding, it's causing the level of the water to increase. And so we see over the last half of the 20th century an increase in this natural rate of sea level rise. And then this here represents some of the future predictions of what sea level rise could look like. And we'll talk about that in a minute as well. Some of the causes of sea level rise, well, as I mentioned, when you warm up water, it expands a very tiny amount. We wouldn't notice it in a glass of water or even in your swimming pool, but when you take 70% of the Earth's surface covered by water and you heat that up, you're going to notice when it starts expanding. And so sea level rise in part is due to this thermal expansion, but also the warming planet is causing ice melt. So mountain glaciers are melting at alarming rates. Ice caps and continental ice sheets are melting and beginning to, some of them are collapsing into the ocean. So all of these effects, the thermal expansion, as well as the additional volume of water being added to the sea due to ice melt, is what we're calling eustatic. It's just a fancy word for sea level rise, eustatic sea level rise. So those are all different components of the actual sea level rise itself. But one thing that people sometimes don't know is that also the land itself is moving, either up or down. And that, again, is a natural process. In parts of New England and parts of the northern U.S., the land is still rebounding from an ice age 12,000 years ago, which seems pretty amazing. But I used to live in Minnesota for a while, and every once in a while we'd have an earthquake. Well, Minnesota is not a tectonic zone, but it's just because the Earth is still releasing the pressure from 2 miles or 3 miles of ice that was on it, you get these little earthquakes. So you can have this uplift due to this rebound, or you can have a sinking of the land, because if we are pulling groundwater out at a high rate, it can cause the land to sink. So there's a lot of different processes that cause the land to either rise or sink at very low rates. But those two things added together, the sea rising because of thermal expansion and because of additional water, and the land subsiding because of different processes, both add together to create this sea level rise that we're talking about. So this shows a map, or a graph, from one of the more recent research groups that have been trying to estimate what sea level rise could look like in the future by these two researchers here, Vermeer and Ramsdorf. This was put out in 2009. And here, this red line is observation. So this is the sea level change that we have seen in, since about 2000. And then these different colors, the yellow, the blue, the green, are based on what a computer model says sea level rise could look like in the future. So when the IPCC, the Intergovernmental Panel on Climate Change, gets together, they look at all the current research, and then they have to figure out, well, what's the future going to look like? Well, we don't know what the future is going to look like, so they figure, all right, if population grows this much, if we use this much energy, if we reduce our fossil fuel emissions this much, you know, this is what the future could look like. So there's like 40 different, what they call scenarios into the future, and each of these scenarios depends on assumptions related to what our global behavior is going to look like. So this A1FI is the business as usual scenario. If we just continue what we're doing, growing at the rate we're growing, using fossil fuels at a continuing rate, it's the higher scenario. The B1 scenario is a lower scenario. So if we decide to reduce our fossil fuel use and begin using more renewable energies, we would see lower carbon dioxide emissions into the atmosphere. And so based on that, we would see different warming because of those additional greenhouse gases. And so the A1FI, this yellow band, represents, well, the yellow line represents the middle of that band of what sea level rise could look like by 2100 under that scenario. And so that's around 140, 150 centimeters, which is around 5 feet of sea level rise with the band. So there's a lot of uncertainty or a lot of error associated with these estimates. So that's why the bands they're just not a line, but they're kind of this wide band here, because it could be higher, it could be lower. And then the B1 scenario, the same thing. The green line represents the middle point of that scenario, but then you've got this wide band. And of course, the bands of uncertainty or error get wider as you get farther out into the future. Same thing with weather predictions. You know, we can predict the weather tomorrow pretty darn good. But if we try to predict the weather for this Memorial Day weekend, well, there's still a little bit of slop in. You know, it could be different than we're predicting right now. It's just so that's the kind of uncertainty we're talking about. And so when we did this mapping, when we tried to figure out what sea level rise would look like, what the implications of sea level rise could look like for coastal communities in Boston Harbor, I mean, how do you pick a number when you have a range of uncertainty that big? Well, we picked a low number, 2.5 feet, which is at the bottom part of the uncertainty range for this B1, the lower scenario. And we picked a higher range number, 5 feet, which is towards the higher end, but not the highest projection for sea level rise in the future. And we said, okay, we'll look at a best case and a somewhat worst case scenario and see what it means for sea level rise and flooding. So what does this change in sea level rise mean for Quincy and communities around here? Well, certainly if the sea is rising, then along with that is a change in the tide heights. So as mean sea level increases, so does high tide and low tide. So places that weren't being flooded before may become flooded even on a daily basis, depending on how close you are to the high tide. So you could see impacts on basements and sewers and piers and wetlands and low-lying areas. And then there is that, you know, that astronomically high tide that we hear about regularly. It happens once or twice a month, where we get a high tide that's even higher than the typical high tide. Well, then when that occurs, then we just get more flooding, more of the above. But the real concern that we wanted to investigate, Chris Watson and Paul Kirshen and I forgot to mention Paul, I'll mention him in a minute, was what happens when sea level is rising and then you get a storm that comes in at the same time. Even if you don't have a change in the storms, even if the same kinds of storms continue to affect us periodically, if you have a higher sea, those storm surges are going to be riding in a higher sea level and are going to be able to reach inland further. And so that was one of the main concerns that we had in this mapping analysis. So so here's our little schematic. We're all, used to looking at low tide and high tide, low tide and high tide. It happens every day, twice a day. And then every once in a while, we get this astronomically high tide, which we decided, since we're New Englanders, we call it the wicked high tide. It's a whole lot easier to say, right? So when the wicked tide comes in, we still are pretty okay along the coast because we're used to that, right? We're all used to the tides changing, and we're all used to that once or twice a month we'll get an astronomically high tide, the spring tide. And usually if we have any kind of coastal protections, that is built to accommodate that. But what happens when you have sea level rise? Well, now low tide with sea level rise is more in the range of high tide. And then high tide and sea level rise is more in the range of the wicked high tide. And then you get wicked high tide with sea level rise, then you start having concerns. So you could see that even once or twice a month with sea level rise, even without any storms, you could begin to see that you might have some impacts due to this. So when a storm comes in, there's a lot of wave action. It builds, it pushes this wall of water that comes in, and it can be a few inches or it can be a few feet. So when that storm surge comes in, it comes in on top of whatever tide level there is. And so if we get a storm at low tide, it's no problem, right? Because that's well within. Here in Boston, we have a 10-foot tide range from low tide to high tide. So if you get a big storm surge of 5 feet at low tide, you won't even notice it. It isn't even up to high tide yet, right? If you get a storm surge at high tide, well, since we're used to our protection is usually is conservative, we're still not too concerned. But once you start getting storm surge at these astronomically high tide, that's when we hear the warnings of coastal flooding possible. But then you add sea level rise on top, and then that's when we're concerned that even the things that we have protecting us along the coast may not be adequate to prevent the flooding that could be caused when we have wicked high tide with sea level rise and a storm surge on top of it. If you don't believe that these kinds of things could happen, well, this is a picture that was taken by Bud Riss, who runs the aquarium, the New England Aquarium downtown. This is Central Wharf. This is a trash can. Typically, they're not designed to be submerged. But this is just high tide back in 2009, and Central Wharf was actually submerged underwater just at high tide. So we're beginning to see in low areas of Boston and surrounding areas that the tides, and anybody who drives down Morrissey Boulevard now, you see the signs almost regularly now that flooding is possible just because of the tide. So it's happening. We're starting to see it. So when we wanted to do mapping for Quincy, for Boston, for other areas, we looked at these two scenarios, the 2.5 foot, which is the low range of possible sea level rise, the 5 feet, which is the high range of possible sea level rise, and then we wanted to see what flooding would look like with an extreme coastal storm, and we picked 5 feet. The so-called 100-year storm surge is about 4.9 feet, so 5 feet's a nice round number. And the blizzard of the century, the blizzard of '78 was around 1.45 feet, well, 4.5 feet, almost 5 feet. So we figured a 5-foot storm surge give us a good idea of what an extreme event would look like. And we showed everything happening at this wicked high tide, because of course if it happened at low tide, there's no reason to map it, right? So as engineers, I'm an engineer, Paul Kirshen, the person we work with, is an engineer. We're always looking to protect against the worst case scenario, so we chose wicked high tide. And then you'll notice on the maps that I'm going to show you, not only do they show the extent of flooding, but they also show an estimate of the depth. So that's where this little stick here that always steals the show comes in. So, but you guys came up with a really nice, I meant to mention over there on the wall there, you can see 2.5 feet and 5 feet and 7.5 feet, which is a 2.5 foot sea level rise plus a 5 foot storm surge. And the same thing is on this stick. So on this side, we have 5 feet. So 5 feet is right about there. And here's 2.5 feet, and that's where I've got a little sticker. I don't know, you guys all have your stickers. And then here's the, here's the stick. I'm going to move out here a little bit. So when you see yellow on the map, it means 0 to 2 feet. So wader, bring out your waders. If you see this kind of pinky color, it means 2 to 4 feet. So chest waders at least. If you see orange, you probably better be in a boat. And probably, if you see blue, you probably just not ought to be there. So this gives you an idea of sort of the three-dimensional aspect of these maps. And people always tell me that this is really helpful in understanding because, you know, 5 feet, I'm 5'3", so if we get 5 feet of storm surge, I'm swept out to sea. That's for sure. So I'm going to leave that. Oh, okay. You want to say? Yeah, sure. Okay, so that's our little legend, vertical legend on the maps. And then we always like to start by showing what Quincy used to look like. So here's a map, what, in 1890 and 1900s, around the turn of the century. Here's Quincy Bay, here's Squantum. I don't know, that must have been a road, huh? But probably you people from around here know a whole lot more than I do. But this is what Quincy used to look like back around the turn of the century. Here's a map of what Quincy looks like now. This is an aerial photo from when? 2008, so pretty recent, 4 years ago. Wollaston Beach is along here. The map, I'm sure you looked at the map out here, but I believe we're right here. And so this is a map of 2.5 feet of sea level rise, just sea level rise itself. So you can see anything yellow essentially would be flooded at that 0 to 2 feet. So wader or boots depth. So along here, just along some of the edges of the salt marsh areas, some of the areas around Marina Bay. Here, of course, this is UMass Boston where I work. But not too much. At 2.5 feet of sea level rise, at wicked high tide, at the astronomically high tide, we don't see a lot of surface flooding. But the thing that this doesn't really show is the kind of subsurface impacts that we could get. So if you ever look at a storm drain outlet, it's usually right at the high tide mark. And so if high tide ends up exceeding that, then the edges of the storm drains could be flooded, and therefore water wouldn't have any place to go when we get a storm. Any of you have basements that are close to sea level rise might have an impact on that. So we could potentially have a lot of subsurface impacts, even though we don't see a lot of surface flooding under 2.5 feet of sea level rise. Here is 5 feet of sea level rise. So here we start seeing a little bit more colorful map. So our maps are pretty, if nothing else. So here's Marina Bay, here's Wollaston Beach. Quincy Center is here. I think we're right in there. This is the area that are they building the new high school, or they're filling in, no, they're putting in a track, right? So this area right here is that big construction area right down there that you can see right now it's wet, right? And there's a lot of wetland right around there, Phragmites. So this area, that's that area right there, going to be flooded fairly substantially because the blue is greater than 4 feet. Down, I guess this is the shipyard here. Just trying to orient you. Here's Squantum. So even low parts of Squantum and this area, this industrial park area over here, Marina Bay, all these things could be flooded. Now this would happen, this is at the astronomically high tide. So once or twice a month with 5 feet of sea level rise, these places could be flooded. And so that would be a nuisance at best and probably pretty disruptive at worst. But then if you take a moderate level of sea level rise, which is 2.5 feet, which is the most reasonable or the most accepted number for sea level rise in the future, and you add this 5-foot storm surge on, that's when you start really seeing the flooding impacts. So where you see the pink, it's 2 to 4 feet. Where you see some orange, it's 4 to 6 feet. And then the blue areas inside the land are more than 6 feet. So now you start seeing areas, very large business, commercial areas being flooded. This area that's just down the street here, flooded even more, coming up this little creek area. Squantum, the wetlands all around, those beautiful salt marshes around the Squantum area, all inundated. Even parts of the shipyard down here, So everything basically right along the coast is vulnerable to sea level rise, on top of the subsurface impacts that we've talked about. And the thing that our maps don't account for yet is wave action. So this is just assuming that the water's coming up sort of in a still manner, still water. So you get wave action on top of that, and then you have impacts that could go even further. So what are some of the implications then about this future climate change? Well, we know on top of sea level rise, we're also likely to see some additional rainstorms, more precipitation events. So we could see additional flooding from stormwater, and when I say reduced hydraulic gradients, the engineers know what I'm talking about here. If the outlet elevation water increases, there's not as much slope for the water to flow down, so you don't have as much driving force for the water to flow in the storm drains, so you can have more flooding, and it backs up further inland. Damage to infrastructure and property, so any of the property that's in these flooded areas could get wet, could be impacted by that, or also by wind and wave action. Business, transportation, well, we all know, anybody driving down Morrissey Boulevard knows that, it doesn't take much to disrupt traffic, right? Much flooding. So business and transportation disruption could be major, especially during a storm surge, and you can't get in or out to some areas. And, we have impacts to health and well-being, which I don't really have much expertise in, but we know that climate change also has some implications with respect to our health and well-being as well. So the question is that the reason we're calling together these meetings and giving this information is not to make you feel depressed or scared or all those things that we all feel whenever we think about this. It's true, it's very depressing, very scary, but we still have time to do something about it. So we have time to do mitigation. Anybody know what mitigation means? Can someone explain what mitigation means when we're talking about climate change? Yeah? Okay, how? How do we lessen the impact? That's a good question. Anybody got any ideas? What are some of the things?
We usually have a trade-off of some kind. The party that wants to do something for people who are impacted.
Ah, right. I see what you're saying. Yeah, when we talk about like wetland mitigation, if someone wants to fill in a wetland here, they have to build a wetland over there. When we're talking about climate change mitigation, does anybody know what are some of the things that we're already doing to try to? Huh? Okay, population control. That's always a hot topic. No cars. So driving more fuel-efficient cars, emitting less CO2. So mitigation, when we're talking about climate change, is related to reducing that CO2 emissions that we're pumping into the atmosphere. So becoming more efficient. I mean, if you just insulate your house, you use less fossil fuel, right? It costs you at the onset, but you save a lot of money over the long term, and you also reduce your emissions substantially. Driving a more fuel-efficient car reduces the CO2 emissions. We could all stop breathing, but that wouldn't last very long. So that's probably not a good mitigation strategy. But, working with your renewable energies, energy conservation, energy efficiency, those are the mitigation strategies that Boston, and I'm sure that Quincy and many of the surrounding communities are already implementing. And many of the mitigation strategies also have economic benefits as well as energy benefits and climate change benefits. But then the other side of the coin has to do with adaptation. So there are many impacts or some level of impacts that are going to happen no matter what we do right now, because we've already started this train running, and it takes a while for the train to come to a stop, right? Even if we were to stop emitting CO2 into the atmosphere right now, we've already started climate change processes, and so we would still have to adapt to some level of climate change. And that's really true to the mid-century. What we've done, the climate change impacts that we're already seeing now, we're going to continue to see at least through mid-century, regardless of the mitigation strategies that we have right now. But it's towards the end of the century that what we do now can really reduce that range of uncertainty I showed you in that graph, that wide range. We can reduce that range to the lower end by the actions that we take now. So the adaptation part of it is how we try to protect ourselves from the impacts of climate change that's already ongoing.